Wow, that's it must be raining. This is downright intimate. Maybe you can move to 310, you know, that's... all right. No doubt about it, we have been talking about dynamic programming. And in dynamic programming, we solve a problem by constructing a DAG plus a function. A DAG is going to be something like this. Where an edge means that in order to compute the value here, you have to apply this function to the values here and here. All right? So the whole cleverness in devising a dynamic programming algorithm. So, first of all, it's to start suspecting that this problem is susceptible to dynamic programming, can be solved by dynamic programming. It's one of these problems for which you can find a DAG and a function, okay? It's not an exact science. You have to think about the problem enough to realize that in order to solve it, you have to carry with you this particular value, all right? And then the point is that once you have defined this function, the DAG is already determined, okay? Because the DAG, it is the DAG of the arguments of this function. And in some sense, the program writes itself, and the analysis is trivial. Okay, this is what always happens. This is what is very special about dynamic programming. When we are talking about a DAG, these nodes are the sub-problems. All right? And so far we have seen a few DAGs. There are many styles of dynamic programs. And for example, in the longest increasing subsequence problem, the DAG was something like this. The longest increasing subsequence, okay? The first problem we solved. Well, you remember, we put the numbers down in the natural order, the order in which they were given to us, and we draw an edge from here to there if this is bigger than this. Okay? That's the longest increasing subsequence problem. So that's one DAG we have seen. Another DAG that we have seen is, of course, the alignment DAG, or if you wish, the edit distance DAG. Okay? Another DAG, remember, is the knapsack DAG, where instead of saying that this is less than this, we have an edge from here to there. If this is one of the numbers given to us, AI, and this is x, and this is x plus AI. If the difference between these two numbers, and remember, we have all numbers here, equals to that. And this gives rise to the algorithm, the pseudo-polynomial, as we called it, algorithm for knapsack, okay? Now, when we have knapsack where you cannot reuse elements, where every element must be used exactly once, it turns out that we must remember something else. We must also remember which elements we have used, all right? And this is done by another trick. We take this DAG and we transform it into a multi-layer DAG. It will take n+1 such DAGs. And now, instead of this going this way, it goes diagonally in every layer. Okay? Sorry, diagonal, I guess, in the appropriate layer. And you also have things going down like that here. Okay? And this tells us the layer at which we are, reminds us of the number of elements which we have already taken into account. Last time, we also did the chain matrix multiplication DAG, which is special. There, the sub-problems are what? Are not prefixes, as in usual, but they are substrings of the data, all right? So we are given a bunch of objects, matrices in this case, in one of your problems, words, okay? And basically, we have to solve the problem for every substring of the data, okay? Then the DAG is essentially this. Okay? Where basically, this subproblem, for example, is this substring, okay? Stands for this substring. And the dependencies, the DAG, no, I should draw it the other way around. The arrows go up. And so on. The dependencies are these lines and also the telescoping things. Okay? So it quickly becomes a mess, but what you have to remember is that there are n square subproblems. But to solve every each subproblem, you potentially have to look at n other subproblems, and so the total number of the total time required is n cubed. Because we discussed that once you have the DAG, you have exactly, you know precisely what is the time required. It is the number of edges in the DAG, okay? And if you think a little bit, you can also find the memory required, okay? Another common thread, a minor detail, but it's important, that unites all these dynamic programming algorithms is that when you compute the value at every subproblem, you must also remember how to reconstruct the solution of this problem, okay? So you must, you know, if you don't do that, it's like running Dijkstra and in the end getting a number, okay? 79, okay? Tells you nothing. You must remember how to get back and reconstruct the optimum solution. And it's always an easy way to do that. The easy way to do that is at each node, at each subproblem, you have a mean or a max, okay? In some sense, every subproblem is, if you take any subproblem here, it is a contest between the incoming vertices, okay? The vertices with incoming edges. And so you have to remember the winner. So from here, you have a pointer to the particular node who won this particular contest. And if you do that, you will be able to reconstruct the optimum solution in the end. All right? You just follow the pointers back, and this tells you how the optimum solution is constituted. So that was sort of, a quick review of what we know, what we have seen so far about dynamic programming. This is our last lecture on dynamic programming. Another thing that comes to mind, every time we write the equation or the function for dynamic programming, there is one, we are computer scientists, there is one very attractive alternative. Why don't we write a recursive program, all right, with this particular recursion? And that is a dangerous thing to do. Recursion works for divide and conquer. And the reason it works for divide and conquer is because divide and conquer is a trivial special case of dynamic programming. Divide and conquer is a special case of dynamic programming where the subproblems you have to solve have nothing in common, okay? In other words, if you call this and then you call that, they will never meet again, all right? That's why you do this, you have this elegant analysis that gives you these super fast algorithms. Here, the subproblems are interweaved in intricate ways, okay? And you cannot separate them. So you cannot do recursion. If you try, you'll get an exponential algorithm that will give you garbage, okay? So, but of course, there is a way out. You can do recursion with memoization. We all have seen that, right? So recursion is a bad idea. No, but how about recursion with memoization? You can do it. It will work. Fine. What's the disadvantage? The disadvantage is that there is overhead, okay? Too many calls means overhead, all right? Function calls. We know that. So that's a disadvantage. There is one advantage, that if you do it by recursion, it becomes a lazy algorithm, a lazy dynamic programming. You understand what lazy dynamic programming means? It means the following, that dynamic programming solves all subproblems systematically, starting from the left-hand side and working in the linearized order of the DAG, okay? From left to right. One by one, patiently solves all subproblems. The point is that maybe in order to solve the big problem, the one you are really interested in, you don't need to solve a few of these subproblems, all right? Some of these subproblems are not used in the final solution. Let me give you one very striking example, all right? Imagine that you are about to solve the knapsack problem, okay? And you have this dynamic programming algorithm for solving the knapsack problem. But imagine now that I tell you, I give you data, which are like, and the knapsack capacity, let's say it is this, okay? So you are given data that are sort of like this. Let's make it interesting. These are the weights. This is the knapsack capacity. It's obvious that there is a lot of redundancy in this data, okay? For example, the easiest way to see it is you divide by 100 and you have the same, instead of having the weight in kilograms, in grams, you have it in kilograms, all right? I mean, same thing, same difference, right? Not, you just change units. And then suddenly your dynamic program is going to run 100 times faster, right? Because suddenly your numbers became smaller. The point is that this trivial observation, the dynamic programming algorithm which you have written will never make, okay? So, and the dynamic programming algorithm you have written will slavishly create all these nodes one by one, between 1 and 2,000, okay? And we'll go through them, stupidly computing what is the best value with this weight, all right? And the point is that, if you solve this problem not by dynamic programming, not by the iterative dynamic programming, but through recursion and memoization, then because recursion and memoization is a lazy version of dynamic programming, then you would have taken full advantage of the special structure of these numbers. Okay, is this point made? Any questions? All right. So let's see a new kind of problem. Here is a problem called the independent set problem. Okay? So you are given a graph, 10 vertices. And you are asked to find the maximum independent set. Maximum independent set is a set of nodes as large as possible so that no two nodes have an edge between them. Is this clear? Maximum independent set. You want a set of nodes that are independent. Independent means that there is no edge between them. All right? So that's an interesting puzzle. What is the largest number here? 4. Anybody can do 5? 5, okay? So basically you take the center and the 4, right? Is this clear? So, believe me, this is a very hard problem to solve, okay? This is an NP-complete problem. Okay? NP-complete problems are, yeah. Any two nodes. Oh, you're right. You're right. Okay. So, I was completely wrong. What is the? I was impressed that you found it. You know, I had trouble finding the maximum independent set in this one this morning. Okay. So what is the maximum independent set here? Thanks. 3 or 4? Who can do 4? This, what? This, the one below the left? No, that's bad. What this, that's 3. Can you do 4? See what I mean? It's a tough problem, all right? We are going to prove it NP-complete. NP-complete means that it's one equivalent with all these thousands of problems that nobody knows how to solve in faster than exponential, okay? That basically the only algorithm we have is Well, look at every set and tell me which one is independent, okay? That's, all right. But, okay, the last part of this class, we are going to talk about NP-complete problems, all right? I mean, and in fact, we are going to do a little more. We are going to learn the theory of NP-complete problems, and we are going to learn how to still try to solve NP-complete problems, even though we know they're hard, all right? And in fact, traditionally, in this class, we have a kind of contest, okay? It's a project which is a contest, okay? So, basically, we come up with one particular NP-complete problem, obscure enough so that you cannot download from the internet, okay? The best heuristic known for it, okay? And you compete writing good code for it, knowing that it's impossible to do exactly. And also, you compete constructing bad examples, okay? That's a little more evil, right? So you compete constructing bad examples, and the team that has the best code, doing best on everybody else's examples, and their examples crashed everybody else's code, okay, wins, all right? So these are the rules, all right? So in any event, it's not going to be independent set, because that's well known. We'll find an appropriate one. But one of the things we are going to learn there is that there are many graph problems like that one that are impossible to solve. They are NP-complete. But if the graph is a tree, is there, you guys have a, yeah. If the graph is a tree, if the graph is a tree, then you can solve it, right? In other words, there are lots, 99% of the NP-complete problems. If the given graph is a tree, they're easy. They suddenly become easy, okay? They can be solved. And how can they be solved? By dynamic programming, all right? So let's take one modest example. Imagine that this is our graph, and you want to find an independent set, okay? Okay, that's your graph. And this is the graph you want to find the independent set of, the maximum independent set of. All right, so if you want a story to go along with it, here's the story. This is the org chart of a company, and the human resources department is throwing a party, okay? And they want to invite as many people as they can, but they don't want a person and their supervisor to be also invited, all right? So that's the story, all right? So now this can be solved, all right? This can be solved by dynamic programming. There is a particular simple genre of dynamic programming, which is dynamic programming for trees. And I want you to guess what is going to be our sub-problem, our concept of sub-problem here. Right? What is sub-problem, sub-tree, get it? It's a sub-tree. So basically, I will solve it first for this tree, then for this tree, and then for the bigger tree, right? So sub-problem is sub-problem here is subtree. Okay? If you wish, vertex of the tree. Because a subtree is basically defined by a vertex. I want to solve the problem for here down. Imagine that this is the root. I want to solve the problem for here down. Imagine that this is the root, and so on. Okay? So I'm now ready to write the dynamic program. Okay, and tell me if you believe it. For every node of the tree, from the leaves up, we do the following. For every node, we call it V. The maximum independent set in the node, in the subtree rooted at the node V, is going to be what? If V is a leaf, 1. Right? If V is a leaf, the maximum independent set of the subgraph of the subtree rooted at this node is going to be 1, of course. Otherwise, it is the maximum, watch, of two things. Here's how you think. Two cases. I want to find the maximum independent set of this subtree, right? Here and below. Rooted at this node. This is V, my V. Two cases. Either V is in there or V is not in there. Okay? Either V participates in the maximum independent set or not. Okay? So if V does not participate, what is the answer? What do you think the answer is? Yeah? Remember, we are doing dynamic programming, so we have solved the problem for the children, and for the grandchildren, and for the great-grandchildren. So basically, I will have, once I decide that the boss is out, okay, I will find the best independent set in this department plus the best independent set in this department. Make sense? What else, right? So it is either, if the guy is not there, the sum over U child of V of I of U, or if I decide that the boss is going to come to the party, the boss of this subtree, I mean, let's not forget to add the boss, okay, plus what? Sum of what? Grandchildren, exactly. U is a grandchild. U of V, I of U. Right? So, what's the bottom line of this demonstration, all right? I'm telling you that there are many hard problems about graphs in the world out there. 99% of these hard problems on graphs become easy if the graph is a tree. If the graph is a tree, the way to solve the problem is dynamic programming, where the sub-problems are the nodes of the tree, or rather, more accurately, the subtrees rooted at these nodes, okay? And to put it differently, the DAG now becomes this. This is my DAG. That's the DAG, the same tree. Okay? So that's an interesting thing to learn about dynamic programming. It's very useful for solving hard problems on trees. Okay. For our last examples of dynamic programming algorithms, we are going to talk about shortest paths. We are going to revisit the shortest path problem. Okay? So, here is a modest example. Suppose that I give you this graph. This is my start. This is my graph. The shortest path from S to this node is what? Believe it or not, it's this. Okay? Total length 7. So, we know how to do it, we know how to find it, we know everything about shortest paths. Here is the twist. Yeah? Right. Okay. All right. All right? Yeah. It's 3 here. Any questions? So, here is my twist. This path has too many edges, okay? I don't like paths with too many edges, all right? Sort of, you know, if in a network, an extra hop can be a disaster, all right? I mean, you don't want too long paths. So this path may be better, even though it's longer, all right? It has only 2 hops, and we like that. So basically, what you want to find is the shortest path from S with at most k hops. Right? Clear problem? Now, in other words, we are penalizing long paths. We forbid long paths. Incidentally, if we just penalized long paths, you know, in other words, say, if we said we are going to subtract 0.3 for every extra edge used, right? Then what? Would we be able to solve it by Dijkstra? Yeah? You just modify the weights, right? Every edge, instead of 2, you make it 1.7, okay? So it's charged 0.3 for every extra edge used, all right? And then you can solve it. Good. But imagine that we want to forbid paths of length more than 7 or something, okay? Then what? Dynamic programming does it, okay? And now that we have become seasoned dynamic programmers, okay? we only need to write the equation, okay, the recurrence, how do you call it, the function. And once we have that, we're done. All right, I mean, there is, so let's, sorry, we don't have to write it even. We have to define what it does, okay? And once we know what it does, then we can write it, okay? And then the DAG follows from that. The analysis follows from the DAG. Everything is solved. All I have to do is write a simple sentence here, right? So here is my trick. Distance Vk is the length of the shortest path from S to V. We are again in a domain where we have a single source and many things, like Dijkstra, with k edges. Do you want exactly k or less than or equal to k? Either would work. All right, let's say exactly k. The equation will be a little different. Let's say exactly k. So, all right, let's write the recurrence. So if k equals 0, of course, okay, we initialize sort of in the obvious way that the length of the shortest path from S to V with 0 edges is either 0 if V is S, or infinity, because there is absolutely no way to go anywhere else with 0 edges. And then you write the recurrence, which says, I guess, distance of Vk is the minimum of all u, v, all u such that uv is an edge, all predecessors, if you wish, of u, of v, of distance of u k minus 1 plus the length of the edge from u to v. That's it. I'm pretty sure that works. Because to go from S to V in k hops, first you have to go somewhere else with k minus 1 hops, and then you must make a last hop. How to go somewhere else with one less hop, you have already computed it. And your data tell you what is the last hop. So go ahead and calculate this, and you're done. You have to, of course, to optimize, to minimize over all possible next to last hops. That's it. Did I forget something? What is it that you usually forget in dynamic programming? To remember. Sorry? To remember. Remember who won, all right? So we have to have some kind of the predecessor of the previous node in the optimum path of V is the winner U. The U that won this contest is going to be the one who is going to be the next to last stop in the shortest path. Is everybody following? Okay, so I'm giving you a dozen examples, and my purpose is that by the end of the third lecture, I want you to be slightly bored. Okay, so that yes, another dynamic programming example, right? Are you slightly bored? Okay, I think I'll wake you up now. Okay, so that's I'll show you a really wonderful dynamic programming algorithm. Okay, this dynamic programming algorithm solves the all pair shortest path problem. So the last two dynamic programming algorithms I'm going to give you in the next half hour, I think are amazing. They solve, in a clever way, path problems, all right? So here's what I want to solve next. All pairs shortest path. Okay? So far, the shortest path problems we were solving were single source. In other words, we were interested for shortest paths out of this particular node. If we wanted single sink, in other words, if we wanted the shortest paths from everywhere into this node, that would be the same thing, okay? You just solve it backwards, all right? But how about whole pair shortest paths? I want all n square shortest paths in a graph. I give you a graph with weights. I want you to compute the all pair shortest path, all possible n square shortest paths at once, okay? Sort of we know how to do it. We can, the edges could be negative, the weights of the edges could be negative, and so we want, one way to do it would be to do V times V times Bellman-Ford, all right? That would be V squared times Z, potentially V to the fourth. It can be done in a really very simple way, cute algorithm, a little hard to think about, a little hard to invent, a very interesting algorithm. It's called the Floyd-Warshall algorithm. Does it in V cubed. And it's a very simple algorithm, like all dynamic programming algorithms. Why? Because it's three nested loops with a single line body, okay? Four-line program. The catch, of course, is that the loops are nested in a rather interesting way, okay? So, and it takes some thinking and talking to get acquainted with its cleverness, okay? The cleverness of the Floyd-Warshall algorithm. So what's the Floyd-Warshall algorithm? What does it do? We want to do dynamic programming, right? What are we going to do dynamic programming on? Dynamic programming essentially tells us, if you find a parameter and you find a way to make progress on this parameter, that's what subproblem means. Subproblem means problem with some parameter fixed, a limited version of the original problem where you fix some parameter. DAG means that we are making progress in this parameter, okay? We get larger and larger and larger parameters of this sort. So the question is, which parameter do I want to control? We know, and the Floyd-Warshall algorithm is based on a rather weird idea, which you have to look at the algorithm for a few minutes for it to start making sense. Yeah, that's actually a clever way to do it, and kudos to Floyd and Warshall who independently discovered it, okay? All right. So, the shortest path from I to j. Okay? So the question is, what is this parameter going to be? Is it going to be I, where I start? Then this would give me this algorithm. Is it going to be j, where I end? That will give me this algorithm also. What is it going to be? It's going to be something else, okay? It has to be something in the middle. What can it be in the middle? So here's an amazing idea. These are called intermediate nodes, right? Okay, they are the nodes that the shortest path has to use. Okay? So, in principle, the shortest path from I to j could use all n minus 2 other intermediate nodes. You realize that I and j cannot appear here, right? Because if they do appear, this means you have a negative cycle and forget it, all right? I mean, so it's not a good sign. So I and j cannot appear there. So intermediate nodes, not I and j, right? So here is an amazing idea. Imagine that we slowly find better and better and better shortest paths by increasing not the index of the source, not the index of the sink, but something else. Which intermediate nodes you can use, okay? In the beginning, we say no intermediate nodes, okay? And then you say, okay, for you, I'll allow you to use node 1 as intermediate node. And then you say, all right, you can now use node 1 and node 2 also. Then node 1, node 2, and node 3. In some sense, you are sort of, you are slowly opening the valve of the intermediate nodes that the solver can use, all right? And the paths become better and better, okay? And in the end, you have the shortest path. Because you have flooded the whole thing, and you can use all possible intermediate nodes. And the only question is this helpful for dynamic programming? Does this enable to write a nice equation? So that's our next. But I mean, I hope I made clear the idea, the basic idea. The basic idea is that the progress to be made, the sub-problems to be solved, so sub-problem I, k, shortest paths using as intermediate nodes only nodes 1, 2 through k. So this is very weird, all right, because you and I know that the indices of the nodes have no meaning, okay? We just assign them at random, all right? And yet here they acquire meaning, okay? They are an arbitrary way in which we order the allowed intermediate nodes, okay? And now I can write and here is the picture, right? Which will immediately enable me to write the program. To go from I to j, using k, using intermediate nodes 1 through k, there are two ways to do it. Either use k or not use k, right? And since I made k explicit in my picture, I know that all other intermediate nodes are less than or equal to k minus 1. In other words, these paths are intermediate nodes from I to k using shortest path from I to k using no intermediate node smaller than k minus 1. Bigger than k. And the same here and the same here, okay? So for these paths, I'm only allowing intermediate nodes 1 through k minus 1. And this picture is the function, the equation, and the loops are exactly what you would imagine. So let me write the program here. That's the Floyd-Warshall algorithm. So what do you do? How do you start? You have to initialize. So you say that the shortest path from I to j using intermediate nodes 1, 2, 3 up to 0, in other words, no intermediate nodes, okay, is what? Is 0 if, is the length of, to go from I to j, actually that's it. The length from I to j, because this is the only way to go from I to j. And of course, if our graph does not have an edge I to j, this is infinite. If I cross j, this is 0, all right? But what I'm saying is that this is our data. It only comes at initialization. And then what do? You do the following. For k equals 1 to n, for j equals 1 to n, for I equals 1, for j equals 1 to n, you do the following. That distance of I, j, k is the minimum of two things. Distance of I, j, k minus 1, comma, distance of I, k, k minus 1, plus distance of k, j, k minus 1. No data structure, no heaps, no priority queues, nothing hidden, I guess, except for the winner, for the prev that we need to remember. Nothing hidden here, just a single line triple loop. Except the order of the nesting is sort of clever, right? I mean, the outer loop, which is the dynamic program, the soul of the dynamic program, the parameter k, which tells us which subproblem we are solving right now, is extremely cleverly chosen, okay? As I said, distance of ijk is the shortest way to go from I to j, not going through any intermediate nodes that are numbered higher than k. The range of intermediate nodes, okay? That's what, in other words, anything less than k is allowed. Less than or equal to k. Any questions? Yes, yes, absolutely works with negative edges. How are you going to find out? Okay, the question was, does this work with negative edges? Absolutely, it works with negative edges. There is nothing there that would not work with negative edges. Of course, we know that if we have negative edges, there is a potential disaster, a potential pitfall, potentially the graph is defective. What? It may have a negative cycle, right? In the Floyd-Warshall algorithm, how do you think we detect if there is a negative cycle? No. Can you think? Why in the Floyd-Warshall algorithm we have on our fingertips whether it is a negative cycle or not? Remember, this is going to return to you a matrix of numbers, okay, where the ijth entry of this matrix is the shortest path from node I to node j. Why do I know immediately if there is a negative cycle or not? Where do I look? Exactly. I look at the diagonal of this matrix. If there is any negative number there, this means that there is a way to go from node 7 to node 7 with negative, right? If the entry dist of 7, 7 is negative, here it is. I have a negative cycle. Actually, all the entries in the diagonal that correspond to negative cycles will have negative numbers there, okay? Everybody understands this? That since this works for negative numbers, there is no reason why not. We never use positivity in order to write this recurrence. We must detect negative cycles. Fortunately, it's very easy. You just look at the diagonal. The diagonal, which shows the shortest cycle, if you wish, from I to I. Every node in the diagonal will hold the shortest cycle from I to I. If this shortest cycle is negative, bingo, okay? The graph has a negative cycle. We can punt. All right? Any questions? All right, so here is a bonus. Yeah. Right, yeah. Yes. And by a length, I mean, if there is no edge, it's infinity. If I equals j is 0. Right? I mean, what makes this algorithm slightly boring is that once you get the right idea, the initialization has to be what it has to be. And the nesting of the loops has to be what it has to be. And the body of the loops has to be what it has to be. Right? I mean, there is no second way about it. Okay? It's very difficult to write this dynamic program in any other way, right? Except for this. Okay, so here is something I want you to remember. Imagine this comes up. I'm sure. How many of you have taken 162? I bet you that you had to solve this problem that I'm going to tell you. All right? It's the following. It's sort of a data structure that tells you, is there a directed edge from I to j? Okay? You are given a directed graph, and all you want to know, is there a directed edge from I to j? Why might you want to know that, okay? Because maybe you want to make j wait for I, okay? And if I is waiting for I plus 1, I plus 1 is waiting for I plus 2, I plus 2 is waiting for j, and j will wait for I, you have a cycle and you have a deadlock, all right? And therefore, you really need to answer this question often, all right? I mean, so, how do you do this? There is a very neat algorithm, which what it computes, basically, if you have this graph. Okay? This graph you can of course represented by this matrix. Right? Then from this you can, let's call this graph A, this matrix A. Then you can from this go to which is what you want, okay? You want to know that, yes, there is a path. Is there a directed, sorry. Is there a directed path? Sorry. So you are given the all directed edges, apologies, and you want to ask, is there a directed path from I to j, right? And if you have this matrix from this graph, if you wish, from this is this graph. This is called the transitive closure. Of the graph. Because it's transitive, okay? If you can go from here to here and from here to here, you can go directly from here to there. If you wish, think of it this way. You have a city. You know whether the city, consider it as a set of bus stops, all right? You know that there is a bus stopping in this bus stop, and next stopping in that bus stop. That's a graph. What is the transitive closure of this graph? It is the graph that tells you, can I go by bus from this bus stop to that bus stop? Okay? That's what you want to do. The bonus is that the Floyd-Warshall algorithm solves this problem. Okay? Watch. I'm going to rewrite it slightly, to edit it slightly. The distance from I to j is 0 if no edge, and it is 1 if edge. Okay? Exactly like this. And then I do this. For k equals 1 to n, for I equals 1 to n, for j equals 1 to n, I do the following. It is the OR of these two. Not the mean, the OR. And instead of plus, I put n. That's it. Okay? I make 5 edits, and my shortest path algorithm, which is Floyd's algorithm, becomes the transitive closure algorithm, which is Warshall's algorithm. Okay, these two people, these two folks, in the 60s, discovered this algorithm for 2 different applications. And then people noticed that it's the same algorithm. Yeah? Because this will take you much longer. Okay? Right, yeah. So basically, you want to solve it. Yes, I agree with you. You could do n-depth first searches. Okay? Sure, you can do that. This is much more elegant. Okay? N-depth first searches might actually be faster. Okay? Unlike the shortest path problem. But most people use this, okay, when they want to find the transitive closure. There was another question, yeah? Say again? What's exponential? Yeah, yes, you can actually do that, yeah. So you see what he's saying? that the way you can calculate this is by raising a to powers, okay? This is true, all right? But let's not talk about it. Okay, so are you ready for the last, our last dynamic program, okay? This one solves a really tough problem. How many of you have heard of the traveling salesman problem? Okay, we'll solve the traveling salesman problem today, all right? So what's the traveling salesman problem? It's the world's hardest problem. You are given a bunch of cities okay? A bunch of cities on the map, and what you want to do is you want to find the shortest cycle that joins them all, okay? The traveling salesman tour. Okay? That's a really tough problem. Of course, it's NP-complete. Like the independent set problem we saw before. It's NP-complete. There is an important difference between these two problems. The independent set problem, at least I can solve it in 2 to the n time, okay? This, the exhaustive algorithm, is slower. How much time does it take? It takes n factorial, right? Because I have to, in principle, I have to check all possible permutations of the nodes, all right? In order to solve it. So, the question is there a way to drop this down to something like 2 to the n, all right? Can I solve it? Of course, it's an NP-complete problem. I cannot hope to solve it. But can I at least make it not harder than the independent set problem, which I know I can solve in 2 to the n, right? Can I make it into a lesser exhaustive algorithm, all right? And there is a clever algorithm that does that. It was discovered in 1970 by Held and Karp. Karp is Richard Karp, the professor here at UC Berkeley. And all I have to do is, now that we understand dynamic programming inside out, all I have to do is write for you a definition, okay? What my function is going to be. All right? And here goes. Obviously, since I have 2 to the n in my sites, I better use sets of cities, all right? Here is the trick. In order to solve the problem of finding shortest paths with few hops, I had to remember how many hops I have made, right? Everybody remembers that? To find the shortest path that does not have too many hops, I have to remember the number of hops I have done so far. Unfortunately, the traveling salesman problem is tougher. It's not enough to remember the number of hops you have done. That's not enough. What do you have to remember? Exactly which hops, exactly where have you been? What is the list of cities? The complete set of cities that we have visited so far. That's what you want to do. And it is the concept of set that will enable us to solve this problem in 2 to the n time and therefore accomplish our goal. Okay? So here is, suppose that you have a set of subset of the cities, and city 1 we assume that city 1 is is the hometown of the traveling salesman, is where he starts the tour. And the traveling salesman is incapable of visiting a set of cities without first visiting his hometown, all right? So we always assume that 1 is in S. And now I'm going to write the equation, right, the definition. L of Sj, where we assume that J is in S and J is different from 1. In other words, we have a set of cities, more than 2, it contains 1, and J is another city in S. And L of Sj is the length of the shortest way to start from 1, visit all cities in S, and end up in J. That's the trick. Okay? That's the trick. Just define L sub Sj to be the length of the shortest way to start from city 1, visit all cities in S, and end up in city J. And of course, if I have everything, all the L of Sj's, I can solve the problem. And of course, from smaller L of Sj's, I can find the larger and larger and larger. This is my sub-problem. Okay? I don't even need to write the algorithm, but I will. Right? So what's the algorithm? It says initialize, I guess. So it says for all S in increasing size, so we start with all sets of 2 cities containing 1, of all sets of 3 cities containing 1, then all sets of 4 cities containing 1, and so on. For all J in S, J different from 1, in other words, for all possible endpoints, that's J, we do this. L of Sj is the minimum over all I in S, I different from J. So what is this length of the shortest way to start from 1, visit everything S, and end up in J? Well, there must be some other set in S that is the next to last hop. Okay? Let's call it I. So it's the minimum for all such I of the length to go S minus J to visit, start from 1, visit all cities except for in S, but not J, and end up in I, and then you have to go from I to J. That's it. It's the minimum of this expression over all possible next to last stops in the tour of the set S, starting from 1 and ending in J. That's it. And in the end, I have to do something like return the minimum over all I, over all J, of the length So the best tour, I guarantee you, is going to be the minimum overall J of the best way to go start from city 1, visit every city, end up in J, and then returning into 1 to close the loop. And that's the algorithm. One of the pleasures of writing a dynamic programming algorithm is that it's always trivial to analyze it. It's nested loops, right? So, what are the nested loops? Here is a for all sets, 2 to the n. Any other nested loop? Yes. For all j, n. Any other nested loop? Yes, this one. It's the minimum over many things, so n squared. Anything else? No, that's it. N squared, 2 to the n. Right? Okay. So that's dynamic programming. All right. The only advice I want to give you about dynamic programming is solve problems. Okay, practice solving problems. And we have a few due tomorrow.